And now we are at example 2. And so after looking at my example 1 with explanations along each of the steps like that, as well as some explanations at the end of after I put the steps together, in this particular example, I will only focus on the order of the steps, and we're gonna focus on the highlighted steps that can get a problem, that can get a testing hypothesis problem done. All right, so let's now spend some time looking at the wording description of this example 2. So a sample of 396 cell phone users shows 300 of them are iPhone users. So obviously it's the same problem with the example 1 that we have done previously. And now from this sample right here, at significance level 0.01 is the sample showing strong evidence that proportion of iPhone users is less than 85%. Okay, so it's only a different problem. This example 2 is different from example 1 only in a way that we are testing a different hypothesis statement right here. So right from this wording, we want to prove that the proportion of iPhone users is less than 85%. So now on my writing board, we can call P to be the proportion of iPhone users and so in this way, according to the statement that I highlighted in the wording description, then we are proving that P is less than, we want to prove that this proportion of the iPhone users is less than 85%. Okay, so that's just a direct translation of the worded statement that we saw in the wording description. And this is the same as saying that P is less than, we want to prove that P is less than 0.85. And so now upon successfully translating the statements highlighted in the wording description into a mathematical equation this way, then we now can see that this is, according to what we've learned from the general lecture, this is going to be our hypothesis, the alternative hypothesis, H1 right here. So now I have H1 can be successfully nailed down as a statement saying we want to prove that P is less than 0.85. And so again, according to what we have learned from the general lecture, anytime that we have already successfully identified H1, the alternative hypothesis, then we can easily from there write down our null hypothesis by simply restating the statements here but substituting the inequality with the equal sign. So instead of saying P less than 0.85, here the statement in H sub 0, the null hypothesis, says P equal 0.85. For this test that we're about to do right here, looking at the alternative hypothesis where the inequality is pointing to the left, this testing procedure that we are doing is regarded as the left tail test. And we will see how being a left tail test will connect with the details that will be explained, that will be delivered in the later steps. And so now back on the wording description of the problem here. Now let's extract information regarding our sample. So right here in the beginning, it say a sample of 396 cell phone users shows 300 of them, or the iPhone users. So this statement here is indicating for me that we have a sample size being 396. And in this sample, at size 396, we found a count. So in 396, we found a count being 300. So this is going to be our sample proportion. It's the proportion of iPhone users in our current sample at size 396. And this sample proportion value for calculation in the later steps, we are going to put this in a decimal. I normally round this to 4 decimal places. However, you can watch for the rounding requirements in every problem that you're doing. So the calculation into decimal comes out being 0.7576. All right, so now that we have had our sample proportion value, and this sample proportion value came out from a sample at this size right here. So the next step now is to check to find out whether our sample size here will be a sample size that works for our testing hypothesis. Otherwise, we're going to have to either stop the test or find a different sample at a larger size or at a different sample size that passes the requirements. So the requirements is as following. With this sample size that we're currently having, 396, it is going to be multiplied with the value being claimed in the null hypothesis. So that value here is 0.85. So I am going to multiply 396 with 0.85. And we want this product to come out with a number that is greater than 10. My calculation came out for this product being 336.6, and it is a value that is greater than 10. So this sample size has already passed one of the two requirements. So we put a check mark there. Now, but we have one more requirement check to find out. So from the same sample size for our sample, 396, we are going to multiply with 1 minus 0.85. And so again, 0.85 is the value that is stated in our null hypothesis, is claimed in our null hypothesis. The calculation here comes out being 59.4, which is again above 10. So the sample size we're doing here passes another requirement. So one sample size this time has passed both requirements. Multiplying the sample size with these two separate quantities right here, both came up with a count above 10. So now upon having our sample size, upon realizing that our sample size has passed the two requirements, we are now ready to advance to the next step of the testing hypothesis problem here. So this next part is something to be aware. So our sample that we're using here, the sample proportion that we're using here, is only one value of all sample proportions at size 396 existing out there. So this random variable capital P hat 396 here generally represents the proportion of iPhone users in a sample, in any sample. So our sample is one among them. So the proportion of iPhone users in a sample of 396. And so now knowing that our sample is one among this population of the proportion of iPhone users, then upon realizing that our sample size here has passed the two requirements, then this distribution of sample proportion, again, this is a further information extremely beneficial to know. All sample proportions here at size 396 can be placed on a bell curve. And definitely our sample will be one value on this bell curve as well. This bell curve will have a center at 0.85. 0.85. So after seeing the two example problems from example 1 up to this point right here, the center of the bell curve will always be that value that we have stated in our null hypothesis. This bell curve will have average spread, sigma p hat being calculated as following. It's a square root expression, and what we have here, 0.85 times 1 minus 0.85, and divide that quotient, that product, by 396, and the entire quotient is inside the square root. And again, this is the bell curve that represents all sample proportions at size 396. So my calculation showed that this sigma p hat after the calculation here will come out being 0.0179. I use 4 decimal places in a lot of these sigma p hat values. However, make sure you watch for the rounding requirements for any of the sigma p hat value in each one of your problems. So this calculation again comes out being 0.0179, and that's our average spread on this bell curve. And so now, having realized that our sample proportion is on this bell curve, so now precisely speaking, we know that this sample proportion must be placed somewhere on the left hand side of our bell curve center. So the bell curve center is here at 0.85, and so our sample will appear somewhere to the left hand side of the bell curve. So this is where I can label my sample value right here, p hat being 0.7576, and that's this value right here at the arrow pointing to it. And so now, upon realizing that our sample can be placed on a bell curve, the next step here, we are going to calculate the z-score for our sample. So I optionally use a subscript p hats, indicating that the z-score we're finding here is the z-score particularly for our p hats that we're using. But you are not required to use that subscript. So z-score for this sample is found by 0.7576 subtract 0.85. That is the difference between our sample value and the center of the bell curve. And we're going to divide that by 0.0179. This is the average spread value on our bell curve right here, the sigma p hat value. Calculation came out for this z-score being negative 5.16, and allow me to write that negative sign in red ink right there. So that's the step after realizing that our sample proportion can be placed on a bell curve. So the two steps I place here in this little space is more like a step that we need to be aware about, but we don't formally have to carry through the step. But then this z-score step here is a step that is critically required after the step where we have checked this, whether our sample size will be a working sample size. So now, having z-score calculated, the next step now is calculating the p-value for our sample. Because any testing hypothesis problem will need to depend on the p-value to decide whether we have strong evidence or not strong evidence. So p-value for this test is done by firing up that probability calculation. We want to find a probability where we can find a sample proportion at size 396, being this time, since the inequality in the alternative hypothesis is pointing to the left or as I have indicated earlier, this testing hypothesis problem is ran as a left tail test. So the inequality in our statements here, in our probability calculation, must be a less than or equal. It's a left tail inequality. And we want to find among all sample proportion at size 396, we want to find one that's being less than or equal to 0.7576. So this is the value that came out from our sample proportion. So this is how we formulate the setup for p-value calculation. So now with this probability problem setup right here, we realize that this is a bell curve problem. That probability statement is equivalent to a shading area on this bell curve where we are shading to the left hand side of our p hat. And so now if we're looking at the picture over here, p hat is on the left hand side of the bell curve center, and the area, the p value we are calculating, is the shaded area to the left hand side. This is the reason why we call this test a left tail test, because the p value is represented as a tailed area on to the left hand side of our sample value. But so now, upon realizing that our problem here can be proceeded as a bell curve problem, this p-value can be calculated simply as the probability where we find a z-score less than or equal negative 5.16 on the standard normal distribution curve. So z-score negative 5.16 was the z-score, or is the z-score that we have found previously from the previous step right there. And so now it's just a matter of running our normal CDF command from my favorite calculator, the TI-84 calculator. So I will be calling up the normal CDF command. And so now on my calculator here, we're going to go second distribution and look for normal CDF command. For a TI-83 calculator or anyone using an earlier version of a TI-84, after selecting the normal CDF command, the command itself will be printed directly on screen instead of showing the menu as you have seen earlier. And this is where you can go ahead and enter the information about the bell curve. So now back to the calculator that I am using. This time on our bell curve, the area is shaded completely to the left where we don't have a definite low end, but we do have an upper end. So upper end would be here at z equivalent to z-score negative 5.16, and the lower end is indefinite. So we will enter negative 1 E99 for the lower end on the normal CDF command. For the upper end, we're going to enter negative 5.16. And again, anytime that I'm teaching my students to use the normal CDF command, we will always default mu and sigma to 0 and 1. So here I'm simply just going to leave those two values unchanged and ready to run the command. So we're going to hit enter a few more times. And so just like that, for anyone who is using a TI-83, eventually you will type in and complete your command just like that, the normal CDF command, and then type in the lower end with a comma, and then the upper end with a comma, and mu and sigma value here. Now we're going to hit enter. So this is the final p-value that the calculator has given us. And so back on the writing board of mine right here, the command can be completed as -1 E99 with a comma, the upper end negative 5.16, 0 for mu, and 1 for sigma on this current bell curve. And so now the answer came out from the calculator we have seen earlier, 1.2370 211 and E negative 7. So this answer from the calculator really means that the actual numerical answer is a 0.0000000 6 zeros before 1, 2, 3, 7, 0 and a lot longer. So that's just, so this means times 10 to the, this means times 10 to the negative 7. That's what the E minus 7 means. And so round it to 4 decimal places, which I usually do, then this final p-value comes out being 0.0000. And so I usually round my final p-value to 4 decimal places, but make sure you watch out for the rounding requirements for p-value in any of your testing hypothesis problems. And so now with p-value successfully calculated, the next step here is to compare the p-value at 0.0000 with significance level given in a problem. So now on the problem, we can now pay attention to this wording that describes at significance level 0.01. So this is the significance level given in the problem. So now we are going to compare our calculated p-value with the significance level being at 0.01. So this is given, this is calculated from the earlier step. All we have to do now is to directly compare the two values here. So direct comparison shows that my p-value is well below the significance level. So this step in that we compare between our calculated p-value with the given significance level is another critical step. This step is for us to decide whether we have strong evidence in our sample or not. So upon realizing that the p-value is well below the significance level, we can come to a conclusion as following. First thing, our sample is an unlikely sample. And further, being an unlikely sample leads to the fact that our sample proportion is showing or itself a strong evidence. And strong evidence here for us to either reject h sub 0, or in another way of saying we have strong evidence to support h1. And that's ultimately what strong evidence is for. And so again, remind ourselves that the testing hypothesis problem is brought to us simply as a yes or no question. Is the sample, this sample that we're having, showing strong evidence or not? And so just now we have concluded that the sample we have is showing strong evidence to either saying reject h of 0 or support h1. So in that way, the ultimate answer to this question is a yes. Our sample is showing evidence, strong evidence. And here in this video, we are going to look at another example where we're going to be testing a hypothesis about the value of a population proportion. And namely, in this problem, it's the proportion of iPhone users. So let's spend some time reading the wording description of the example here. So according to the wording here, then we are given a sample of 423 cell phone users. So in what it says here, a sample of 423 cell phone users shows 321 of them are iPhone users. at significance level 0.001 is the sample showing strong evidence that proportion of iPhone users is other than 50%. So apparently with this question right here is a sample showing strong evidence. This question immediately indicates that it's a testing hypothesis problem. But now we, as a starting point, we want to tackle down right in this particular wording right here. We want to prove based on the sample that the proportion of iPhone users is other than 50%. And so now on my writing board, again, we can define P to be the proportion of iPhone users. And according to the statement that I highlighted in the wording description of the problem, we want to prove that P is other than. So other than mathematically is represented by this symbol over here. So not equal to. So we want to prove that P is other than 50%. Or in another way of saying, we want to prove that P is other than 0.5, because 50% is in decimal a 0.5. So from this understanding, we are now going to have our alternative hypothesis H1, which says P is other than 0.5. And once again, all of the logical reasoning of how I can see this statement here as the alternative hypothesis is already explained throughout my general lecture on testing a hypothesis. And right from this point right here, upon successfully identifying the alternative hypothesis, we can now arrive easily at the null hypothesis, which is pretty much the same statements here, except we substitute the inequality symbol here with the equal sign. So my null hypothesis is going to read P equals 0.5. All right, so now that we have successfully identified our two hypotheses of our testing hypothesis problem, the statement right in this alternative hypothesis is having an inequality that's saying other than. So in this kind of inequality, it could be a greater than or it could be a less than. And so this test we are about to perform is regarded as a two-tail test, because the inequality here is not only left tail, it's not only right tail, it could be any one of the left tail or right tail inequality. So generally we regard to this right from the alternative hypothesis statements with this inequality, we regard to this test that we're about to use as a two-tail test. So let's now get back in the wording description of the problem and extract out some more information, especially regarding the sample of our problem. So in here it says a sample of 423 cell phone users shows 321 of them are iPhone users. So this very beginning statement where I highlighted has all of that information regarding our sample proportion. So on the board here, I can write it down that we have a sample. We use a sample at size 423. That is our sample size. Now in this sample, among the 423 cell phone users, we have counted and found out that 321 of them as a count are using iPhones or iPhone users. So this proportion here, this ratio here gives us a sample proportion. It's a proportion of iPhone users within our sample of 423 cell phone users. And so this is apparently a sample proportion. Calculation came out in decimal being 0.7589. So I use 4 decimal places for this sample proportion value, but make sure you watch for the rounding requirements in any of the problem that you're doing. So now we have a sample proportion, and again at this sample size being 423. So in the next step, I am going to check to find out if the sample at this size right here will be a working sample for the rest of our testing hypothesis procedure. So in order to do that, I am going to multiply the sample size 223 with 0.5. So this is the value that's claimed or stated in our null hypothesis. So the sample size of our sample multiplied with the claimed value in the null hypothesis. This product came out, according to my calculation, 211.5. And it is a product that is greater than 10. And then, so that tells us that our sample size has passed one of the 2 requirements. And so now the same sample size we are going to multiply with 1 minus 0.5, which is exactly 0.5 again. So needless for any calculation, this product will come out again being 211.5, and it will surely be greater than 10. So with the 2 quick calculation steps right here, it verifies that our sample at this current sample size right here will pass the 2 requirements in order for us to move on for the rest of the testing hypothesis problem. So I put a check here on each one of the 2 requirements there. And now this is something to be aware about our sample. Our sample proportion is one sample among infinitely many other, where generally we regard to any of those sample proportions in this way as a random variable capital P hat for 23. So the meaning of this is the proportion of iPhone users in a sample of 423 cell phone users. And now after realizing that our sample size has passed the 2 requirements, now we know that this distribution of all sample proportions at size 423 can be placed on a bell curve, including our particular sample. Our particular sample can now also be found on this same bell curve as well. This bell curve will have the center at the value that's claimed in the null hypothesis. So in this way, it has to be 0.5 being the center of this bell curve. Any value on this line right here is a sample proportion at size 423. This bell curve, like any other bell curve, will have an average spread, where symbolically we call that sigma p hat, standard deviation of this sampling proportion, this sampling distribution of the sample proportions. Sigma p hat value for this bell curve can be calculated by the formula square root of 0.5 times 1 minus 0.5 in the parentheses and inside the square root, and we divide that by 423, which is the sample size. My calculation came out showing that sigma p hat, or the average spread of this bell curve, equals 0.0243. I use 4 decimal places for my sigma p hat in this problem, in this particular video lesson, but make sure you watch for the rounding requirements in any other problems when it comes to sigma p hat. And so now on this bell curve, it is surely guaranteed that our p hat can also, our particular sample proportion can be found somewhere on this bell curve. So according to the way how we have already known about this bell curve, this is something to know about our distribution of sample proportions. Then our sample must stay somewhere to the right hand side, because that's the value it has right there. So our sample proportion must stay somewhere to the right hand side of the center on this bell curve. And the value is again 0.7589. So this information regarding the bell curve, where our sample belongs to, is something for anyone to know before we proceed to the next step. The following step will be an important step. Now that we know our sample belongs to a bell curve, from where the sample stands on this bell curve, it will have a z-score. So let's now go ahead and spend some time calculating the z-score. Z-score for our sample. I optionally use a subscript p hat, which is not really required for a lot of instructors out there. Our sample is at value 0.7589. To find the z-score, we're going to subtract the center of the bell curve, 0.5, and we divide this difference by the average spread of the current bell curve, so 0.0243, this value that I have found previously. Final calculation comes out to be positive 10.65 as the z-score for this sample proportion that we're using. So from where what it says here is that from where our sample stands on this bell curve relative to the center of the bell curve, it is at z-score positive 10.65. And I highly recommend to indicate the sign of your found z-score in red ink. So I would write positive 10.65 here. I use 2 decimal places for any of my z-score, but make sure you watch for the rounding requirements in each of your problem that involves a z-score. And so now the next step is to calculate the p-value, just like any other testing hypothesis problem we have done. But this time we want to be a little more cautious here. The p-value calculation, it is important to understand how to set up the p-value calculation when we are doing a two-tail test. So now this is a two-tail test. It's neither a left tail nor a right tail test. So here's how we can set up the p-value calculation. We are going to find a probability that we can find a sample proportion at size 423 that is greater than or equal to the sample proportion 0.7589. So let me take a quick pause here, and I'm not saying that we have completed the setup for the p-value calculation yet. But so this inequality right here is associated with a right tail test. I'm assuming that you have already seen my video, the earlier videos where I have shown how to run a right tail test. So this inequality is indicating that our test is a right tail test. But this actual test right here is a two-tail test. It could be a right tail or it could be a left tail. So what made me decide to use this inequality depends on the sign of the z-score. So in this problem, it is extremely important that we calculate z-score before we start setting up the p-value calculation. So since z-score here being a positive, because again, back at this starting point right here, the test we're doing here is a two-tail test, which could be a left tail or it could be a right tail. So z-score being a positive leads to myself deciding to use this right tail inequality. So again, positive z-score, we use the right tail inequality. But then in the end, the test here truly is a two-tailed test. It's not really a right tail or it's not really a left tail, even though I set up a right tail test calculation here, but it's not simply just a right tail test. So in order to achieve the exact p-value calculation for a two-tailed test, we are going to multiply that overall probability by 2. So this is a 2 times. So 2 times the probability, 2 times the right tail probability. So as a picture, we can think of this overall p-value as following. The right tail probability here is the area shaded to the right of our sample, but only one side, that's the right tail. So now doubling that means we can think about another area exactly opposite, on the opposite side right here, where we would be shading as well the area completely to the left of that. So now having the double here means we double this shaded tail area to create this double region right here. So that's how we're calculating p-value in a two-tailed test. And let me open another remark right here. This is a remark. If z-score for our sample in this calculation was a negative z-score, then we would go p-value equals 2 times the probability where we're looking for sample proportion at size 423, but being less than left tail inequality, less than the value 0.7589. So this is a different scenario if, as I said, if the z-score turned out being negative, then this is what we would do. And so now at this point, we are ready to get into calculating this overall p-value. This probability itself here, before multiplying by 2, is equal to the probability that we can find a z-score greater than or equal to 10.65 on our standard normal distribution bell curve. And then we're going to multiply that probability by 2. And so now it's just a matter of running to find this probability on the z-score curve right here. We just run the normal CDF command. Now on my calculator, we're going to retrieve the normal CDF command, second variables, and look for that option saying normal CDF command. And so with this version of the calculator I'm using, the command gives me a menu. On a TI-83 calculator or some earlier versions of the TI-84 calculator, after executing the normal CDF command, you will see the normal CDF command being printed directly on your home screen instead of seeing the menu as you have seen earlier. And now back on this version of the TI-84 calculator, allow me to show. So low end for this interval. Recall again that we're looking at this interval where it's greater than or equal to 10.65, or it's this area shaded to the right hand side of the value. So we have a low end, but we have an indefinite upper end. So on the calculator, low end here, I'm going to enter positive 10.65. That's low end. Upper end here will be an infinite upper end. So for the calculator, we use 1E99. And I'm going to default mu and sigma to 0 and 1, because again, we are only running this normal CDF command on the standard normal distribution bell curve. I'm going to hit enter a few times. And so for the TI-83 calculator or any earlier TI-84 calculators where you have to type in and complete your command, then you're going to type in the lower end first, with a comma, and then the upper end with a comma, and then mu and sigma value, then close the parentheses. And now on whichever version of the TI calculator that you are using, we can hit enter. The answer is now the p-value for us. This is the probability value. So on my board, I need to complete my command right here. 10.65, comma 1E99, comma 0, comma 1. And don't forget, we need to multiply this probability by 2. So what we saw on the screen, on the calculator screen earlier, is just a calculation of this. The answer, the probability where z-score is above 10.65. So that value came out 8.921077 according to the calculator. 5 by 2 with an E minus 27. And don't forget, we need to multiply this quantity by 2. So this lengthy expression right here from the calculator means it's, this part right here means it's times 10 to the negative 27. So what it says here is that our final p-value must be 2 times 8.921077 and a lot longer times 10 to the minus 27, which is altogether, after multiplying by 2, just 0.000. So this is our final p-value, and we regard to this as a two-tail p-value. So we now have gotten our p-value calculated. So now in the next step, we're going to compare the p-value with our significance level given in the problem, so that it can help us decide whether we have strong evidence in our sample or not. So back on the wording description, the significance level is given right here in the wording at significance level 0.001. So this p-value will be compared directly with 0.001 given in the problem. The direct comparison is telling me that this p-value is well below the given significance level. And so with this comparison result right here, it's now telling us clearly that the p-hat, the sample we're using now, is an unlikely sample. And being an unlikely sample, it leads to the fact that p-hat is showing strong evidence. Okay, and the strong evidence here is for us to either saying that we're rejecting h of 0. That's one way of saying it. Or we can say to support h1. And so now apparently we are having p-hat is showing strong evidence. The wording of the problem here, according to the question of the problem here, the ultimate question here is the sample that we have showing strong evidence. So just now we have proven that the sample is here, is showing strong evidence. So the ultimate answer to that question is yes. Is the sample showing strong evidence? Yes, the sample is showing strong evidence. And here we are at another example where I'm showing a problem in how we can test a hypothesis about a population proportion value. And this is just another example out there where I am going to just focus on the order of the steps, how we can carry out the steps in order to test a hypothesis about the value of a population proportion. So let's spend some time reading the wording description of this example here. A sample of 423 cell phone users shows 321 of them are iPhone users. At significance level 0.01 is the sample showing strong evidence that the proportion of iPhone users is greater than 72%. So in the wording here, again, is the sample showing strong evidence. This is the wording that brings to our attention that the problem here must be a testing hypothesis. But for now, I am going to focus on the following. We want to prove that the proportion of iPhone users is greater than 72%. So greater than 72%. Now on my writing board, we have P being the population proportion of iPhone users. And the wording in the problem was saying that we want to prove P is greater than 72%. So symbolically, it's P greater than 72%. So there's our statement. This statement is the same as saying that P is greater than 0.72 because a lot of times we write percentage as a decimal. So just like that, so now from our understanding from the general lecture about testing a hypothesis, we can now extract or identify for ourselves an alternative hypothesis, H1, which says we want to prove that P is greater than 0.72. And just like that, now we can easily identify for ourselves the null hypothesis, which says P is equal to 0.72. So again, as you have seen, then the null hypothesis is simply just the repeat of the alternative hypothesis, but substituting that inequality with the equal sign. The test we will be doing here is regarded as a right tail test. And now let's look back at our wording of the example to find out some further information regarding our samples. So what it says here, a sample of 423 cell phone users shows 321 of them are iPhone users. So this line right here is telling us all of the information about our sample proportion here. So now from the wording, this is what I know. We have a sample at size 423. In this sample of 423 cell phone users, we have found a count of 321 iPhone users. So this is now regarded as a sample proportion. 321 out of 423 gives me a value in decimal to be 0.7589, and I'm using 4 decimal places for a lot of my sample proportion values, but make sure you watch it for the rounding requirements anytime you're working on your own problem about testing a hypothesis out there. So now that we know some information about our sample proportion, the next step now is to find out if our sample at this current sample size, at this indicated sample size, will be a working sample in order to advance to the next steps, to the rest of the steps on this testing hypothesis problem. And so in order to do that, in order to test in order to check if our sample has a satisfying sample size. We're going to do the following. 423 is our sample size. I am going to multiply with 0.72. So this value 0.72 is the value that being stated in our null hypothesis. The calculation came out giving me 304.56, which is a number well above 10. So that tells me that this sample size has passed one of the two requirements in order to make the test procedures work. Now, the same sample size 423, I am going to multiply with 1 minus 0.72. And again, this value 0.72 is the value being stated in our null hypothesis here. Calculation gave me 118.44 for this product, which is a number well above 10. So now I realize that the sample size, or our sample at this sample size, has passed the two requirements in order to move on to the rest of the testing steps. And so now the next step here is something for anyone to know about our sample. Our sample proportion here is 1 among infinitely many other samples, where I generally regard to any one of them as a capital P hat, random variable capital P hat 423. So capital P hat 423 here is a random variable that represents the proportion of iPhone users in a sample of 423 cell phone users. So in that, we know that our sample is one value among infinitely many values in this population of sample proportion values. And so now at this point, upon realizing that our sample at this sample size 423 has passed the two requirements, then we now know further that this sampling distribution of all our sample proportions can be placed on a bell curve, and including our value right here, our sample proportion is 1 among all of these sample proportion values, so they can all be placed and found on a bell curve. So any value on this line here is a sample proportion at size 423. The center of this bell curve now will be the value that's stated in the null hypothesis. So in this way, center of this bell curve will consequently be 0.72. The average spread on this bell curve here, symbolically sigma p hat, can be calculated by doing the following. Square root of 0.72 inside the square root times 1 minus 0.72, and we divide that by the sample size 423. All of that is inside the square root. Calculation gave me sigma p hat for this bell curve equals to 0.0218. So I use 4 decimal places rounding for my sigma p hat value here, but make sure you watch for your own rounding requirements when it gets to calculating sigma p hat. And so in this way, our sample proportion value can be precisely found somewhere to the right hand side of the bell curve center on this bell curve. So I place a point here. That is our p hat value, and the value for that is currently 0.7589, somewhere to the right hand side of the bell curve center. And so these steps here are good for anyone to know in order to move on to the next step, but they're not critically required. The following step here is going to be required. Now, once we know that our p hat is on the bell curve, then the next step, we're going to calculate the z-score for our sample. I optionally use a subscript p hat here to indicate that this is a z-score specifically for our sample that we use in this testing of hypothesis. So calculating z-score, we're going to go 0.7589. I'm going to subtract the bell curve center, 0.72, and that difference there will be divided by the average spread, the standard deviation of all sample proportions on this bell curve. So that would be 0.0218. Calculation of mine came out showing that this z-score is going to be 1.78 as a positive z-score. And so now I am going to formulate a calculation setup for the p-value of our testing hypothesis problem here. So as the next step. So p-value calculation will be formulated as following. We want to find the probability where among infinitely many sample proportions here, we want to find a sample proportion value that's greater than or equal to 0.7589. And we can check for consistency here by seeing that the test here right from the beginning is regarded as a right tail test. So the inequality in our p-value calculation here is used as a right tail inequality, which is also consistent with the fact that our z-score is a positive z-score. And so now this p-value calculation, this probability calculation is equivalent to a shaded area on this bell curve shaded to the right hand side of wherever our sample proportion is. And so now this probability is exactly equal to the probability where we're looking for z-score greater than or equal to 1.78 on the standard normal distribution bell curve. And so to find this probability, it's now just a matter of running the normal CDF command or any kind of equivalent technology to find the area that's shaded to the right hand side of z-score 1.78 on our standard normal distribution bell curve. So I'm going to turn to my calculator, the TI-84 calculator here. Second variables, and I'm going to bring up the normal CDF command. For TI-83 or earlier, for some early TI-84 calculators, after retrieving the normal CDF command, you will see the command being printed directly on the screen as following, instead of the menu as you have seen earlier. And now back to the calculator version that I am using. We're now going to enter the lower and the upper ends for our interval here. So one more time on the interval of z-score, we're looking at the interval shaded to the right hand side of a z-score. So we do have a low end, a definite low end, but an indefinite upper end. So in that way, for my lower end, I'm going to enter, this is where I enter 1.78. And for the upper end, it's an indefinite upper end, so I'll enter 1E99. And I'll default these two values at 0 and 1 for mu and sigma. I'm going to hit enter a few times. And so now this is how TI-83 or earlier TI-84 calculators can see how they can complete their command right here when the normal CDF command is printed directly on the screen. So we type in the low end with a comma, the upper end with a comma, mu, comma, sigma. Then we close the parentheses. Now I'm going to hit enter. So this is our final p-value for this test, for this testing hypothesis problem. So back on my writing board, to complete this command right here, low end is 1.78, upper end is 1E99, and we have a comma here, comma 0, comma 1. That completes our command. And so now running this, we came to that answer being 0.0375379.306, and a lot longer. I am going to round this final p-value to 4 decimal places. And make sure, whoever watching this video, make sure to watch for your own rounding requirements when you're doing your own problem. So in 4 decimal places, this is our final p-value. So this step is another step that is quite critical over here. We need a p-value in order to decide whether our sample is showing strong evidence or not. So now, once we have calculated our p-value, the next step is to compare our p-value 0.0375 with the given significance level in the problem. So back to the wording of the problem. At significance level 0.01. So now we know that we have a significance level here given to be 0.01. So 0.0375 being our p-value will be compared with the given significance level 0.01. A direct comparison right here is showing that this p-value is well above the significance level given in the problem. And so now, with the p-value being above the significance level, it is telling us a decision as following. P hat is not an unlikely sample, or in another way of saying, nothing unlikely about p hat. And so consequently, it leads to a further conclusion that p hat is not showing, or is not itself strong evidence. Okay, and the strong evidence here is to either reject h of 0 or to support h1. So we just simply don't have p hat is not strong evidence to reject h of 0. Another way of saying is that we failed. P hat fails to reject h of 0 or fails to support h1. That's another way of saying it. And now ultimately back to the wording of the question. We're asked as a yes or no question, is the sample showing strong evidence? Apparently our sample is proven to be not showing strong evidence. So the answer to that ultimate question now is no. Our sample is not showing strong evidence here.